Hello, students. So, today we will continue our discussion that we started on thermodynamics. So, in the last class, we had our brief introduction about the Hess's law of the heat of summation, and we saw how it can be applied to enthalpy, that is the energy change, or to any other state function that are involved in thermodynamics, just like Gibbs free energy, or you can say the entropy, that is S, etc. So in this class, we will first start with the brief recap of our last session, where we ended on our discussion on the Hess's law of constant heat summation. So firstly, you have to get why it is important and why is it relevant. That is the Hess's law. Now, if you see over here, it is a pictorial representation of Hess's law. You can see we have a state that is C carbon, that is solid, with 2 moles of water, that is in gas phase, will produce, if burnt in oxygen, CO2, that is in gaseous form, and 2 moles of dihydrogen. And the entire process really requires 90.1 kilojoule. So in figure, this is figure 1, is a pictorial demonstration of Hess's law of constant heat summation. C plus 2H2O are placed in a box together. This is the first box. And also the state of the materials could be involved in the reaction prior to the reaction, because carbon was solid, hydrogen, that is water, that was vapor, and now it is producing CO2 plus 2H2, which is placed together in a second box that represents the state of the materials involved after the reaction. Now, the reaction arrow connecting these two boxes is leveled with the heat of the reaction. The heat of the reaction is this one, 90.1 kilojoule. Now, we have to take these same materials and place them in a third box that contains carbon, oxygen, and H2. This box is connected to the reactant and product boxes with reactant arrows leveled by the heat of the reaction in equation 3 and 4. The first one is minus 483.6 kilojoule, and the second one is minus 393.5 kilojoule. The picture of this Hess's law actually suggests us that the heat of the reaction along the path directly that connects to the reactant state to the product state is exactly equal to the total heat reaction of the alternative path. So there is a consequence of our observation of Hess's law. It says that therefore net heat evolved or absorbed during the reaction is independent of the path, and it connects the reactant and the product. So this statement will again support that the restriction is always there. All the reactions in alternate path should occur under same pressure and temperature condition. So the entire reaction here happens at a constant T and constant P value, not in a different temperature or different pressure value. So with this reasoning, we can say that we can actually define an energy function whose value for the reactants is not dependent of how the reactant state is achieved or prepared. So that is the value of this energy function of the product state is independent of how the products are prepared. In this case, we choose this function that is capital H, that is enthalpy. If you look at the equation, delta H is equal to H of products minus H of the reactants. That is exactly equal to the heat of the reaction, that is Q under constant pressure condition, which we call enthalpy, because you know delta H at a constant pressure is called the QP, that is heat evolved from the reaction or heat absorbed in the reaction at a constant pressure. Now, it is a state function whose value depends on only the state of the materials under consideration. However, the temperature, pressure, and composition of the materials, only upon this value, that is enthalpy value, depends upon. We start with another example. The enthalpy of a reaction does not depend on the elementary steps, but on the final state of the products and initial state of the reactants. Now you know that H, that is enthalpy, is an extensive property. It is not an extensive intensive one. And so it when the size of the sample changes, it also changes. So enthalpy of the reaction scales proportionately to the moles of the reaction. Now for this reaction, you can see we have two reactions. We have reaction 1 and we have reaction 2. So if we look at reaction number 1, we have H2 plus O2 producing H2O. The second reaction is also the same, but just the way of balancing these chemical equations are different. In the first case, the balancing has occurred by putting a half over here. So that's why it is balanced. Delta H0 is minus 572 kilojoule. And also, if we can balance the equation in a different manner, so that we can put 2 over here in ahead of hydrogen and we are putting 2 ahead of water, then also delta H0 value becomes just the double of the first reaction. That is minus 1144 kilojoule. If you look carefully, that delta H0 of reaction 2 is just double of the delta H0 of 1. So why is it so? Because enthalpy is a state function, though it is an extensive property. And extensive property, as we know, it changes when the size or the volume of the amount of sample changes. So when we had the first equation, we had 1 mole of hydrogen. But in the second case, we have 2 moles of hydrogen. And that's why, since the stoichiometric coefficient of dihydrogen is doubled from equation 1, then that's why the delta H02 is just the double of the delta H01. So this is the clear-cut indication that enthalpy is a state function and also an extensive property. Now the sign of the reaction, as I have told you, also gets reversed when the process is reversed. If for this reaction H2 gas plus half O2 gas, we are producing H2O gas, the delta H0 is minus of 572 kilojoule. Then if we switch the reaction, that is reactant becomes product and product becomes reactant. H2O gaseous to H2 plus half O2, we get delta H0 as plus 572 kilojoule. Now, since enthalpy is a state function, it is not dependent on the path. So it does not matter what reactions one uses to obtain the final reaction. Just the initial and the final state of the reactants and products should be the same. So if we have a process A to B, and for which if it is delta H value is X, then for B to A, the delta H value would be minus X in the same unit. So that shows that enthalpy is a state function. And also, if we reverse the reaction for a backward and a forward reaction, the sign of the enthalpy change will just be the opposite one. That's why when the delta H0 for this reaction was 500 and minus of 572 kilojoule, then for the backward reaction, H2O to H2 plus O2 has a delta H0 value of plus 572 kilojoule. So hence we have got a very brief but very distinct idea about the Hess's law of constant heat summation. Now we will move towards the discussion of very important terms that are enthalpies of different types of reaction. So we have to see what are the enthalpies of different kinds of reaction. In chemistry, we have different classes of reaction. We have combustion reaction, we have the atomization reaction, and also we have the bond enthalpy. So there will be specific different kinds of reaction for which there will be some standard enthalpy values. And to show that what are the standard enthalpy values, we have to define each enthalpy value. So they will be very much convenient to address them. So firstly, we will start with our first discussion case, that is the standard enthalpy of combustion. Delta C H minus. So we have this delta CH minus, and this is for the combustion reaction. Combustion reactions are actually exothermic in nature. And since combustion reactions are exothermic, that's why in most of the cases, you will see the delta CH minus value will be less than 0. Combustion reactions are very much important for industrial applications, in rocket science also, and also in the cases of other walks of life. So standard enthalpy of combustion is defined as the enthalpy change per mole of the substance when it undergoes combustion procedure. And all the reactants and products, they are being in their standard states. That's why the notion of minus comes at the specified temperature. So this C over here comes from for combustion. And this minus over here stands for the standard state. So this minus stands for the standard state and the C stands for combustion. So that's why it is termed as the delta CH minus. That means it is standard enthalpy of combustion. So if we take some examples over here, firstly we can take the very common example in our households, that is the cooking gas. Cooking gas in cylinders actually contains mostly butane, which is a straight chain 4 carbon aliphatic hydrocarbon, that is C4H10. Now, during complete combustion of 1 mole of butane, we can obtain the thermochemical equation. I have already told you in the last class that's what it is meant by a thermochemical equation. A thermochemical equation is when we have a entire chemical equation and then we have to balance it first, and then we have to specify what is the change in enthalpy. So we have butane, that is C4H10, and it is a gas at room temperature. And we have to first burn it in oxygen. During the beginning of our lecture series, I have told you that whenever a hydrocarbon is completely burnt in oxygen, it produces carbon dioxide and water. So we have two products. CO2, that is a gas, along with liquid water. Now, this is just a mere equation, but it is not a thermochemical equation. So for this, firstly, we have to balance the equation, and we have to specify the delta CH minus value. So here we have 4 carbons on the LHS. So we'll put 4 over here to make the carbon atoms same on both sides. Now we have got 8 plus 1, 9 oxygens and 2 hydrogen. But on this case, we have 5 hydrogens. Sorry, 10 hydrogen. So that's why you have to put a 5 over here. That will make it 10 hydrogens. But now we have 4 into 2, that is 8 plus 5, that is 13 oxygen atoms on the RHS. So to maintain the oxygen atoms number over here, we have to put a 13 by 2 coefficient over here. So that makes carbon, hydrogen, and oxygen completely balanced. Now this is a completely balanced equation. And for this balanced equation, the delta CH minus value is minus of 2658 kilojoule per mole. The delta CH minus value is negative. That shows that it is an exothermic reaction. Actually, all the combustion procedures we will deal with majorly, they will be a combustion procedure and those will be exothermic in nature. So now we have got the entire thermochemical equation, that is C4H10 plus 13 by 2 O2 produces 4 moles of CO2 and 5 moles of H2O. Here, if we have to calculate the delta Ng value, we have to be a bit careful, because for calculating the delta Ng value, that is the change in number of moles of gaseous substances in the entire reaction mixture, we have to see that the three components are gaseous, but one is liquid. That's why we will omit that. Now the reactant gaseous mole is 4 and the product gaseous moles are 1 for butane and 13 by 2 for oxygen. So now we have 4 minus 15 by 2. That is minus of 7 by 2. So this is the delta Ng for this reaction. In examination, it may comes for this reaction, you have to calculate delta U value. So delta H is equal to delta U plus delta Ng RT. So delta U will be delta H minus of delta Ng RT. The delta H value is given to you, that is minus of 2658 kilojoule per mole, plus it will be delta Ng RT. Delta Ng value is calculated over here, that is minus of 7 by 2, plus we will have the R value, that is 8.314 joule per mole per Kelvin, and we will multiply this with the temperature. Whatever will be given, if it is 25 degrees Celsius, we will multiply by 298 Kelvin. So another example is there when glucose is actually undergoes combustion and it produces even more heat, that is 2802 kilojoule per mole. So if we see the reaction of glucose burning or combustion, glucose chemical formula is C6H12O6. Similarly, when glucose is burnt in oxygen, it produces CO2 and water. Now we have to first balance this. Now on the left hand side, we see the number of oxygen atoms is 6 and 2 plus 8. Number of hydrogen is 12. So we'll put a 6 over here to make the hydrogen atom same. Now the oxygen atoms become 6. We have a carbon over here 6. So we have to put a 6 over here to make the carbon atoms same. So it will be 12 plus 6, that is 18 oxygen. We have a 6 oxygen over here already. Now we will put a 6 over here to make it 6 plus 12, that is 18 oxygen. Now the entire equation is balanced. The delta CH value of this reaction is minus of 2802 kilojoule per mole. So it produces even more amount of energy than the first one does. Our body also generates energy from the food, and the entire same overall process is as simple as combustion. Although the final products are formed after a very series of complex biochemical reactions involving enzymes. So these reactions may be very much complex. These are all biochemical reactions which requires a help from the enzymes. And then the final product is CO2 and water liquid. So that's how our body generates energy. We will now look into a specific example for a more clearer view. So now we have one combustion. We have a combustion procedure when we have 1 mole of benzene. One mole of benzene is here, which is kept at 298 Kelvin temperature. And it is at 1 atmosphere pressure. So under this condition, the combustion of 1 mole of benzene takes place. And after combustion, as you know, CO2 and water are produced. Because any hydrocarbon, if we burn in oxygen, because of the combustion procedure, it will produce carbon dioxide and water. So, and the heat produced is 3267 kilojoule per mole. So this much amount of heat is actually liberated. Now we have to calculate the standard enthalpy of formation delta FH minus of benzene. The standard enthalpy of formation of CO2 and H2O are given as minus 393.5 kilojoule per mole and minus of 285.83 kilojoule per mole. So this is the amount of heat that is generated from the reaction. The given things are, we have to calculate delta FH minus of benzene. We'll denote benzene as C6H6. So this is actually required from the reaction. And the things that are given to us is the standard enthalpies of formation of CO2 and water. So we have the delta FH minus of CO2. The value is given as minus 393.5 kilojoule per mole. And the same for H2O. Is given as minus 285.83 kilojoule per mole. These two values are given to us and the amount of heat that is liberated is given. Now we have to calculate the standard enthalpy of formation of benzene. Now for this, the formation reaction of benzene is given by 6 moles of carbon plus 3 moles of H2O producing a liquid benzene. We have to calculate delta FH minus of the reaction. If we have to calculate the formation reaction of benzene, the enthalpy, we have to see how from the elements benzene is formed. So benzene is made up of carbon and hydrogen atoms. For carbon, the mother state is carbon in solid state, and we have hydrogen that is in the H2 form and is the mother state. And so it produces C6H6, that is benzene. That's why for solving this kind of numerical equation, you have to first have a clear idea about the molecular formula of the reactants and the products. And then only you can write the equation and then you can be able to balance those. Now we have to balance this. Have 6 carbon atoms on RHS. So A6 will be here. And we have 6 hydrogen atoms. So it will be 3. This is the balance equation. 6C plus 3H2 produces 1 mole of C6H6. That is a liquid. Now we have to calculate the delta FH minus of this reaction only, which we will term it as reaction 1. Now this is a reaction that the data is actually given for the combustion reaction. This amount of heat is generated from benzene for a combustion reaction. Now what will be the equation for the combustion reaction? So we will write it C6H6 plus O2 produces CO2 and water. As it is very much evident that a hydrocarbon, if combusted in the air, it will produce carbon dioxide and water. On the right hand side, then also we have to balance this equation. We will put a 6 over here to make the carbon atoms same. So now we have this. We have to make this 3 because the number of hydrogen atoms should be same. And so it is now 6 into 2, that is 12 plus 3, 15. There is 2 oxygen over here. So we will have the 15 by 2 parameter here. So now in this case, we have the second equation, which is the combustion reaction. And for this combustion reaction, the delta CH minus is given as minus 32767 kilojoule per mole. So 3 minus of 3267 kilojoule per mole is the energy that is released from the combustion of benzene in ideal oxygen. Now the two values that are given to us are the enthalpy of formation of CO2 and enthalpy of formation of H2O. So we have to write even two more equations for the enthalpy of formation of carbon dioxide and that of water. So firstly, we will write the enthalpy of formation of carbon dioxide, which is a very simple reaction. We do not even need to balance this because it is already balanced. C plus O2 produces CO2. That is the enthalpy of formation of CO2 in the standard state. You see, for carbon, the elemental state is this one, and for dioxygen, it is O2, and both, if combined, produces 1 mole of CO2. And that for water is also very simple. For water, it is H2, and we have O2, which produces H2. For balancing this equation, we will put a half ahead of oxygen, which will take care of it. So now we have these two equations also. We will name it as equation 3, and we will name the last equation as equation 4. For the first equation, the value is given as minus of 393.5 kilojoule per mole. For the fourth equation, we will have the value minus of 285.83 kilojoule per mole. Now let's have a look at all these equations. We have now got many equations. we have equation 3, we have 4. So we have two equations. But here you see in the first case, we have to have the value of these 6 carbon and 3 hydrogen. And we have C6H6 that is in the product side. So how we are going to obtain this? So firstly, we have to first get rid of the equations over here. Because in this equation, you see here, in this case, the carbon atoms has a stoichiometric coefficient of 6. But in this case, we have a stoichiometric coefficient of 1. Here we have a stoichiometric coefficient of 3 ahead of hydrogen, but here we have 1. So to make these equations feasible, to ultimately give the first equation, we have to carry out some multiplication, subtraction, and addition procedure. And now we have got these two. So now we have to multiply the first equation by 6. And also we have to multiply this equation 4 by 3. And then what we will have? So if we multiply this equation by 6, we have to multiply this by 6. And you have to multiply, if it is by 3, then we have to entirely multiply it by 3. So if we multiply this by 6, we have 6 over here, we have a 6 over here, and we have a 6 in the product side. And the value will be here, this value will be minus of 2361 kilojoule per mole. Also, you have to multiply this equation by 3. So we'll put a 3 over here, we'll have a 3 over here, and also a 3 ahead of the water molecule. And if we perform the multiplication here, it will be around minus 857.49 kilojoule per mole. So what do we do here? Actually, we have got the first equations as CO2, H2O2 in all the cases. But the ultimate equation we need is 6 carbon and 3 hydrogen. That's why we had to multiply these two equations by 6 and 3, so that by adding or subtracting them, we can ultimately get some value of the equation 1. So now we have got some modified equations, these 3 and 4, and then we can sum up these two equations. So what will happen if we simply add this equation? So now we will simply try to add this. So what happens if we add equation 3 and equation 4? So we have 6C by addition of 3 and addition of 4. So if we add equation 3 and equation 4, we will have the equation 6 carbon plus, now you see over here the oxygen terms are common. So if the oxygen terms are common, we will add the stoichiometric coefficient over here. So here it is 6, here it is 3 by 2. So 6 plus 3 by 2 counts for 15 by 2. This is the oxygen stoichiometric coefficient. And also we have 3 moles of hydrogen. And this produces 6 moles of carbon dioxide and 3 moles of water. And now if we calculate all these things, we'll end up getting this equation 6C plus 15 by 2 O2 plus 3 moles of hydrogen produces 6 moles of CO2 and 3 moles of H2. But we have to keep this thing always in mind whenever we are adding up the equation. Also, we have to add this delta H values too. So here is a delta H value, here is a delta H value. And if we have to add these two values, we will ultimately get the value of the delta H value of formation will be minus of 3218.49. So we have got the equation which we will term as equation number 5. Now we have to go to the second equation. Here you see, here we have the second equation. In the second equation, we had all these parameters: benzene 15 by 2 O2, 6 CO2 and 3 H2O. And the value of the combustion heat was minus of 3267. So as we have learned from the SS law of constant summation, that if we reverse the equation, the delta CH minus value will just be the positive one. So now we will simply reverse this equation, that is 6CO2 plus 3H2O producing C6H6 plus 15 by 2 O2. So we'll reverse equation 2 as 6CO2 plus 3H2O producing C6H6 plus 15 by 2 O2. And the delta H value F minus of this will just be the opposite one. So it will be value will be reversed. It is plus 3267 kilojoule per mole, because it was negative in this first equation of 2. We will term this equation as equation 6. So now you see over here we have very good sets of equation, because we have a 15 by 2 O2 on the left hand side and we have a 15 by 2 O2 on the right hand side. We have 6 CO2 on the left hand side, and also we have 6 CO2 on the right hand side, and 3H2O are on the opposite sides. So what we have to do to solve these kind of equations? In these kinds of solving equation, we have to make the equations so that, and we have to rearrange them just by reversing them or adding them, that we have to have the cancelled out terms. So now in this case, if you see, if we can add this equation 5 and equation 6, simply there will many terms be there which will be completely cancelled off. The first one will be 15 by 2O2 and the 15 by 2O2, because it is in the LHS, it is in the RHS. So it will be cancelled out. Then comes 6 CO2 and 6 CO2, and also 3 H2O and 3 H2O. So all we are left with 6 carbon, 3 hydrogen and this benzene. So ultimately we have got our equation 1 back. So we have got the equation 6C plus 3H2 produces 1 mole of C6H6, which was our first equation that we had to get, this one. This one we have reached equation 1 with the help of equation 2, 3 and 4. So what did we do first of all? Firstly, we had the equation 3 and 4, but then we had to multiply these two equations by suitable numbers to get the value of this one. So then we have got 3 and 4 and simply we added them. Now we just reverse the equation 2 and then added to the addition of 3 and 4. And ultimately we get all the terms as cancelled out. So the more you will practice on this, you will try to understand how we can add or subtract the equations, so that ultimately the parameters or the substances we get are our required one. We required 6 carbon and 3 H2 on the left hand side. That's why I kept them on the left hand side for the entire numeric. And also on the right hand side, we have the benzene molecule. We have to keep the benzene molecule. And that's why I have to reverse the equation so that these terms will be cancelled out and all we are left with these equations. So likewise, we have the delta FH minus of this and this one. We have to simply add them. And if we add them, equation that is minus 3218.49 plus 3267, we ultimately get the value that is 48.51 kilojoule per mole. So this is the delta FH minus value of benzene. So ultimately, we have got our desired answer, that is delta FH minus of benzene, that is 48.51 kilojoule per mole. So likewise, in this case, whenever we are dealing with such problems, you have to look at the given equation. You have to also see what is the ultimate equation that we want to obtain, and then with the help of all the equations and just by reversing them or adding them suitably, we can ultimately get the actual equation, and from this we will get the value of the delta H enthalpy, that is the standard enthalpy of formation of the required product. Now we will move to our next set of discussion when we will discuss the enthalpy of atomization, the symbol being delta AH minus. This delta AH minus, this A stands for the atomization. And the minus state stands for the standard state. Now, what we actually mean by the atomization procedure? For this, I will start with a very trivial example, that is the reaction of hydrogen gas to two hydrogen atoms. We have hydrogen gas and we are producing two hydrogen atoms. The delta atomization of H, that is the delta AH minus value of the reaction, is positive in nature. That is 435 kilojoule per mole. We have seen that in this case, the hydrogen atoms are formed by breaking HH bonds in the dihydrogen. So in the left hand case, we had a HH bond in the dihydrogen. This is dihydrogen molecule, and then we are breaking it and we are producing two hydrogen atoms. One is this and another is this. Two hydrogen atoms we are producing, and that's why it is termed as the atomization procedure. And that is an endothermic procedure, which is very much obvious from the delta AH minus value, that is 435 kilojoule per mole. So from dihydrogen molecule, we are breaking the hydrogen-hydrogen bond, and that's why the process is called the enthalpy of atomization. It is actually the enthalpy change on breaking 1 mole of bond completely to obtain the atoms in the gaseous phase. Now, in case of diatomic molecules, Like dihydrogen, that is the example we are giving over here. The enthalpy of atomization is also termed as the enthalpy of bond dissociation. So the bond dissociation enthalpy and the atomization enthalpy will be very much similar or same in case of diatomic molecules. Suppose we have a diatomic molecule A2. So we have a AA bond and we have to cleave this bond. Now this energy actually corresponds to the enthalpy of atomization because we are producing the atoms. So different AA atoms to different AA atom will be produced. And also since the bond between A and A is getting broken and it is the only bond that is getting broken, it will be termed as the bond dissociation enthalpy. So it will be delta BDH minus. So for diatomic molecules, these two terms are same for diatomic molecules. Diatomic molecules, there are only one bond, and in this case, the bond dissociation enthalpy, the BD actually stands for the bond dissociation, and this A stands for the atomization. The other example, if I have to give you on atomization, it will be from methane to carbon and hydrogen. So we have a methane molecule in the gas phase. We are producing carbon atom and 4 hydrogen atoms. That is the enthalpy of atomization. The value is 100 and 1665 kilojoule per mole. The one thing you have to remember that all the things are actually done in the gaseous phase. Atomization procedure is actually done in gaseous phase. The products are only atoms of carbon and hydrogen on the gaseous phase. Now, if we have to see the following reaction, then it is another kinds of reaction which is termed as sodium solid to sodium gas. So we have a sodium solid and we are producing sodium gas. Now for this reaction, the delta AH minus value is 108.4 kilojoule per mole. Now in this specific case, the enthalpy of atomization is just as same as the enthalpy of sublimation because this procedure is also a sublimation process. So what do you mean by sublimation? I guess you guys know about about this a little bit because in case of sublimation, it is a phase change phenomena where from solid do not stop at liquid but directly we arrive at the gaseous phase. So if you know about the phase transfer or phase change, we have three primary phases of matters. One is solid, another is liquid, and another is gas. If we go from solid to liquid, it is termed as melting. If we go from liquid to gas, it is termed as the vaporization. If we come from gas to liquid, it is termed as the condensation. And if we come from liquid to solid, I guess you guys know it that it is called the solidification. If we go from solid to liquid, we can call it as melting, and from liquid to solid, we can say it as freezing. So these are the procedures. So here, instead of skipping any phase, we are going from solid to liquid to gas and from gas to liquid to solid. Now sublimation is a bit difficult, is a different process. In this case, without even stopping at the liquid phase, a solid directly goes from the solid phase to the gas phase. That is called the sublimation procedure. So in case of sublimation procedure, a solid is directly converted to a gas phase. And here also, if you have a closer look at it, it is a sublimation procedure where sodium solid is directly converted to sodium gas. And the enthalpy is 108.4 kilojoule per mole. And also, if you see in this case, this is an atomization reaction also, because sodium is an atom here in the gaseous phase. So in this case, the enthalpy of atomization, that is delta AH minus, is equal to the delta sublimation of H in the standard state. So in this case, when it was all about the diatomic molecule, we were talking about that in case of diatomic molecule, the enthalpy of atomization is just the same as the enthalpy of the bond dissociation. So here, so that's why in this case, delta AH minus and delta bond dissociation of H minus were same. And in this case, when we are talking about sodium solid to sodium gas, then it was a sublimation procedure. And when it is sublimation procedure, the delta atomization HA minus will be equal to the delta sublimation of H minus. So that's why in many cases, one enthalpy can be converted to another enthalpy. So with this, we will conclude our today's discussion. That in today's discussion, we had discussed about the Hess's law of constant summation, and with a very good example of this benzene combustion in ideal atmosphere, we have come to know the how we can solve the numerical problems here. And also there are two phases, the enthalpy of atomization, that we know that what is meant by this, and there are also different kinds of enthalpy. One is the bond dissociation enthalpy, that we had a brief idea in this class, but in the next class we will learn more on this term, that is the bond dissociation enthalpy, that is delta BDH. This term is very much vast, and we need to have a very clear cut idea on the enthalpy of bond dissociation, because in chemistry, all is going upon is the breaking of bond and breaking of bond. And that's why the bond dissociation enthalpy is very much useful for the understanding of chemistry. And also, then we will move our discussion to the Born-Haber cycle in the next class. And if you guys have any query or any discussion regarding any of the slide, you can ask now.